Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 8. Speaking in Phi, Designing Messages that Survive. Remember the language we are learning. There is one field, Phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When Phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how Phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of Phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. Welcome to the culmination of Book 10.1, Language Fluency. We have learned to read Phi, to see its letters. We have learned to understand its sentences, to recognize its common clauses. Now, we take the most thrilling step. We learn to speak. We learn to encode our own discrete intentions, create a vortex, send a pulse, initiate resonance, into a Phi waveform that can travel through the noisy, distorted world and be understood on the other side. This is the skill of the speaker. You are entering the radio operator's cabin. Before you is a transmitter, a receiver, and the wild, unpredictable channel, the world itself. Your job is to craft a message so robust, so perfectly shaped to the channel's nature, that it survives the journey intact. Scene: the noisy channel. Imagine this. You are in one room. In another room, 50 meters away, separated by thick walls and the bustling hallway, is your partner. Your task? Send them a simple 3-bit command. 1, 0, 1. Perhaps it means activate pump 3. You have a speaker in your room and a microphone in theirs. This is your channel. The air, the architecture, the background noise of ventilation and distant conversation. You could just shout the numbers. But shouting is amplitude modulation. You're changing the loudness. In a reverberant room with noise, loudness gets smeared. Echoes create ghosts of your message. Background sounds drown you out. But you have a more subtle tool. You have a pure tone generator. You can play a steady sine wave, and you can shift its phase. Not its volume, but its timing. You can make the wave jump ahead by a quarter cycle, or lag by half a cycle. These phase shifts are your alphabet. This is phase modulation. Your message is now etched not in loudness, but in the precise timing of the wave's peaks and troughs. This is our starting point. We have a channel, a physical medium with specific properties: bandwidth, noise, distortion. We have a message, discrete, symbolic meaning. We have an encoder that maps message to Phi waveform. And we need a decoder on the other side that can reverse the process, recovering the message from the corrupted received signal. Our puzzle is this: how do we design a Phi-encoded message that survives the channel's noise and distortion with high reliability? How do we speak so the universe, or another listener, can truly hear us? The core challenge. The channel wants to talk back. The first, deepest insight of Phi communication is this: the channel is not a passive pipe. It is an active participant with its own personality. Its personality is defined by its equations of motion, the constraints that govern how Phi evolves within it. In air, sound waves obey the wave equation. In an optical fiber, light obeys Maxwell's equations, modified by the fiber's geometry. Each channel has natural modes, specific Phi patterns, frequencies, spatial shapes, that resonate within it. These are the channel's eigen-solutions. A pure tone at the resonant frequency of a room rings loud and clear. A tone at a different frequency is absorbed. This leads to our central coherence criterion for speaking. The encoded message must be a coherent packet, a Phi pattern that is an eigen-solution of the channel's equations of motion, or as close to one as possible. Why? Because eigen-solutions propagate with minimal distortion. They are the channel's preferred sentences. If you speak in the channel's native dialect, your message travels cleanly. If you try to force a pattern that is dissonant with the channel's modes, the channel will fight you. It will scatter, absorb, and distort your message until it's unrecognizable. Our dissonance indicator is now specific. A message design that excites strong channel resonances, unintended powerful eigenmodes, will be catastrophically distorted. It's like shouting in a cathedral and triggering a deafening echo that completely smothers your original words. The message drowns in the channel's own amplified noise, therefore, are safety railed. The message's energy and spectral content must stay within the licensed coherence budget of the channel. Every channel has a limit to how much coherent structure it can support before nonlinear effects kick in, before the wave breaks, like an ocean wave hitting the shore, or before it couples destructively with other messages. We must know this budget and design our message's intensity of change to stay under it. If coherence breaks, we stop. If coherence returns, we continue. We cannot transmit if the channel is in a state of chaotic resonance. We must wait for it to settle or actively damp the resonances first. The coherence budget for speaking. Before we design a single symbol, we must assess our coherence budget for this communication act. This budget is defined by the channel's physics. 1. Channel bandwidth. This is our frequency capital. The channel can only cleanly support phi oscillations within a certain range of omega, temporal frequencies, and k, spatial frequencies. Our message's spectrum must fit entirely within this licensed band. Trying to send a signal with components outside the bandwidth guarantees distortion. They will be filtered out or converted into noise. 2. Coherence time, length of the channel. This is our stability capital. In a turbulent medium, like the atmosphere or a noisy electrical circuit, the channel's properties, like its effective index of refraction, change randomly over time and space. The coherence time is how long the channel stays roughly the same. The coherence length is the distance over which it stays correlated. Our message must be shorter than the coherence time and smaller than the coherence length to experience a single, consistent channel. Otherwise, part of our message goes through one version of the channel, and another part goes through a different one, scrambling the signal. 3. Signal-to-noise ratio, SNR, budget. This is our clarity capital. Given the channel's inherent noise floor, thermal noise, shot noise, background chaos, how much signal power can we inject? The SNR determines the fundamental limit of how much information we can send, the channel capacity from Shannon's theorem. Our message design must operate within this SNR constraint. If our budget is insufficient, if our message is too broadband, too long, or too weak, we cannot communicate reliably. We must adjust, simplify the message, use error correction, repeat it, or find a better channel. Our coherence gate after transmission is the decoder success rate. We don't just send and hope. We send many test messages, a training sequence, through the actual channel or its digital twin. We measure the bit error rate, BER. Does it match our prediction based on our channel model and SNR? Is it below our acceptable threshold, for example, less than one error in 10,000 bits? The pass-fail rule is strict. If the measured BER is significantly higher than predicted, or above threshold, we fail. Our message design or channel model is flawed. The communication is incoherent. The rollback trigger. We revert to a simpler, more robust modulation scheme. We fall back to a lower data rate. We may need to recharacterize the channel. We contain the failure by not using the flawed design for critical commands. We isolate the problem. Was it the encoder, the channel model, or unexpected noise? The triunity of a message. A message in phi is a triunity entity. It must be crafted in time, space, and motion. Consider a simple phase shift keying, PSK, message on a sound wave. Time echo, the carrier frequency, the steady rhythm of the underlying sine wave. This is the clock of our message. In this 1D sound example, K is the wave vector along the direction to the receiver. But we can also think of the space of the signal itself, its shape in the frequency domain, its spectrum. Our modulation creates a specific spectral shape. The message propagates at the speed of sound, but more importantly, the information moves. The pattern of phase shifts flows from transmitter to receiver. The decoder must synchronize to this flow, this motion of meaning. For a spatial message, like using a laser to paint a pattern of vortices onto a distant screen. The sequence in which vortices are created. The arrangement of vortices on the screen, their XY positions. The scanning motion of the laser beam or the perceived motion if the vortex pattern is rotating. A well-designed message harmonizes these three echoes. A poorly designed one creates conflict. For example, a temporal symbol rate that is too fast for the spatial resolution of the receiver, causing blurring and intersymbol interference. Encoding, from meaning to phi pattern. Let's design a simple message. Our command is 101. We decide to use binary phase shift keying, BPSK. We'll use a clause from our library, a wave clause at a specific frequency omega 0. For 1, we set the phase of this wave to 0 radians. For 0, we set the phase to pi radians, a half-cycle shift. But raw BPSK is fragile. A single burst of noise can flip a bit. So we add error-correcting codes. We don't just send 101. We send a longer sequence that includes redundancy. Perhaps we use a 7-4 Hamming code. We encode our 3 bits of data, plus 1 padding bit, into a 7-bit code word. Now, even if 1 bit gets flipped by noise, the decoder can detect and correct it. But we are thinking classically. In phi-space, we have more elegant tools. Topological encoding. Instead of encoding bits in phase shifts of a wave, we encode them in the topological charge of defect clauses. Send a vortex with charge +1 for 1 and charge -1 for 0, or use a pair of vortices. The beauty of topology is its protection. Small amounts of noise cannot smoothly change an integer charge from +1 to -1. The charge is quantized. The message is robust, until the noise is so strong it destroys the defect entirely, unwinds the vortex. This leads to a prediction. Topological encoding will show an error cliff, near perfect fidelity until a threshold noise level is crossed, then a sudden, catastrophic drop to 0 success. This is a very different performance curve from classical codes, which fail gracefully. Our encoder, then, is a 2-part machine. 1. The semantic mapper translates the symbolic command, create vortex, into a sequence of clause instructions. Generate defect clause with charge +1 at coordinates x, y. 2. The waveform synthesizer takes these clause instructions and generates the actual phi, x, y, t pattern using the grammar from episode 9 to ensure it's a physically realizable coherent packet. It respects the channel's bandwidth and coherence budget. The prediction spine, benchmarks for a better language. Our work builds a prediction spine that lets us test if phi communication offers real advantages. 1. Grammar advantage. A message designed with phi grammar, using valid, coherent clauses that respect the channel's constraints, will have a lower bit error rate after transmission than a random waveform of the same power. The coherent packet suffers less distortion because it fits the channel better. 2. Decoder performance curve. The decoder success rate will follow a predictable statistical curve, like a Q function or an exponential in SNR, based on the channel's measured SNR and the distance of our error-correcting code. If our implementation matches the theory, we have a solid engineering handle on performance. 3. Topological error cliff. As mentioned, topologically encoded messages will exhibit a sharp threshold. Below a critical noise power, BR is a problem 0. Above it, BR is a problem 0.5, random guessing. The location of this cliff is predictable from the stability energy of the topological defect. These predictions are falsifiable. They are the standards we must meet. Falsifiability, the reality check for claims. Here are our falsifiability threads. If a phi communication system cannot outperform a well-designed classical, amplitude-based or standard phase-based system on the same channel under fair benchmark conditions, same power, bandwidth, data rate, latency, then its claimed advantages, robustness, elegance, topological protection, are not realized in practice. The phi advantage might be theoretical only. If blind decoders, without knowledge of our specific codebook, can recover our messages at a rate significantly above chance, then we are not communicating securely. We are inadvertently broadcasting in a universal code. Conversely, if even our design decoder cannot recover messages above chance level from a clean channel simulation, then we are not communicating at all. We're just generating noise. These falsifiers keep us honest. They prevent us from falling in love with a beautiful idea that doesn't actually work better than what already exists. Channel modeling, knowing the terrain. Before we transmit, we must model the channel. We use our measurement skills from book 10.2, which we're previewing here. We send probe signals, short pulses, chirps, pure tones, and measure the response. From this, we build a channel model in our digital twin. Impulse response. For our reverberant room, this is the sound you hear after a single sharp clap, all the echoes and their decay times. Frequency response. Which frequencies are amplified, resonances, and which are absorbed, nulls. Noise spectrum. What does the background noise look like? Is it uniform white noise, or does it have specific troublesome frequencies, like 60 Hz hum? The twin becomes our communication sandbox. We simulate sending our encoded message through the model channel, adding synthetic noise. We run our decoder on the received, corrupted signal. Does it recover the message? We iterate on our design, adjust modulation, add error correction, choose different carrier frequencies, until our success rate in the twin exceeds our target. This is engineering, not guesswork. Lanterns across scales, the universal act of speaking. The principles of phi communication illuminate scales far beyond the sound wave in a room. Cellular signaling. A hormone molecule binds to a receptor. This event is a discrete message. The encoding is the specific 3D shape, a phase pattern in the molecular electron clouds that fits the receptor's channel, its binding site. The decoder is the conformational change in the receptor that triggers a cascade. Noise is thermal jostling. Error correction is provided by the energy landscape. Only the correct shape binds strongly enough to trigger reliably. Middle scale, the internet. Fiber optic communication. Light waves, phi field, are phase modulated with data. The channel is the glass fiber, with its bandwidth, dispersion, and nonlinearities. The coherent packet is a soliton, a special wave pulse that maintains its shape due to a balance of dispersion and nonlinearity, an eigen-solution of the fiber's equations. This is a perfect example of designing a message to be a coherent packet of the channel. The search for extraterrestrial intelligence. If an advanced civilization wants to be found, how might they encode a beacon? A narrowband coherent radio signal, a wave clause, is a good candidate. It's unnatural, persistent, and survives the interstellar channel, plasma dispersion, noise, better than broadband noise. They might use prime number timing or topological patterns in polarization, a form of defect clause, to signal artificiality. In each case, successful communication depends on matching the message's phi structure to the channel's coherent modes and budget. The ethics of speaking, responsibility in the channel. The ethical dimension here is about channel pollution and consent. When you transmit a powerful phi signal, you are not just sending a message, you are exciting the channel. You are injecting energy into a shared medium. Your coherent packet, if poorly designed, could trigger destructive resonances in the channel that disrupt other natural or technological processes. A badly designed acoustic message could shatter glass. A powerful electromagnetic pulse could fry electronics. The safety rail, staying within the license coherence budget, is an ethical requirement. It's the principle of minimal necessary disturbance. You do not shout in a library. You do not flood a radio band with noise. Furthermore, in a network, which this enables, the issue of addressability and consent arises. Are you broadcasting to everyone or targeting a specific receiver? Are they listening for you? Unwanted communication is coercion. The technology to shape phi patterns is also the technology to project patterns onto unwilling substrates, be they electronic, biological, or cognitive. The discipline of clear, consent-based addressing protocols becomes an ethical engineering constraint. Power without coherence is self-destruction, and coherent speaking requires respect for the shared channel and the autonomy of other listeners. A measurement scene, the reverberant room. Let's enact our roadmap's measurement scene. Scene, sending the 3-bit command 101 via phase modulation on a sound wave through a reverberant room. What we measure. We first characterize the channel. We play a chirp and record the impulse response with the microphone. We measure the background noise spectrum. We build a channel model in our digital twin. The pass. We design our BPSK encoded message, perhaps with a simple error-correcting code. We simulate its transmission in the twin, tuning parameters. We then transmit for real. We send the message 10,000 times. The receiver decodes 101 in 9,950 trials. The error rate, 0.5%, matches the prediction from our twin simulation based on the measured SNR and impulse response. The received phi pattern, when unwrapped and analyzed, clearly shows the three distinct phase shifts corresponding to 1, 0, and 1. The decoded beats are random, no better than guessing. The error rate is 50%. Analysis shows why. The chosen carrier frequency coincided with a deep null in the room's frequency response, a resonance that cancels that frequency. Our message was annihilated by the channel's own structure. Alternatively, the reverberation time is so long that symbols smear into each other, causing catastrophic inter-symbol interference. Our design failed to account for the channel's coherence time. The recognition skill, seeing the need for robust encoding. You know you need this skill when you have a clear intent that must survive a messy, noisy journey. Whenever you think, I need this instruction to get there intact, no matter what, you are in the domain of phi communication design. If you look at a channel and immediately start thinking about its quirks, this medium disperses high frequencies. There's a lot of multipath here. The background is very non-Gaussian. And then design your signal specifically to overcome those quirks, you are thinking like a phi speaker. The digital twin, the communication lab. Our twin is now a full communication simulator. It contains 1. A channel emulator that can mimic any measured impulse response and noise profile. 2. A library of encoder-decoder pairs we can test. 3. A performance analyzer that plots BER versus SNR, measures distortion, and identifies failure modes. We stress test our designs here. We simulate fading channels, impulsive noise, interfering signals. We ensure our message is not just coherent, but robustly coherent. It can maintain its integrity in the face of expected channel variations. Enabling the future, the networked civilization. This skill, Shalom, depends directly on the clause library. You must know the words to form sentences. It enables two monumental next steps. 1. Literacy assessment. How do we test if someone is truly fluent? We give them a communication challenge. Design a message to send this command through this simulated channel with the BER less than 10^-4. Speaking is the ultimate test of understanding. 2. Network communication. This is the foundation for building a phi networked civilization. If individual nodes can speak and listen reliably, we can connect them into a web of shared reality, protocols, and consensus. We are moving from solitary observation to social interaction, from literacy to dialogue. Zenodo and the limits of speaking. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers detail the Kammerau lower bound analysis for phase estimation, the fundamental physics-based limit on how precisely you can measure a phase shift given a certain noise level. This is the ultimate benchmark. No communication system, no matter how clever, can reliably decode phase differences smaller than the CRLB allows. This sets the absolute coherence budget dictated by quantum and statistical mechanics. The papers also formalize topological error correction codes and the mathematical structure of channel eigenmodes, turning our metaphors into rigorous design tools. Return to the phi. Let's zoom out. We have taken our third pivotal step. We can read, we can understand, and now we can speak. We can imprint our intention onto the fundamental field in a way that persists through noise and distortion. We remember, there is only one field. Our message is a carefully crafted ripple in phi, designed to resonate with the channel's own nature. Our communication is not a battle against the medium, but a collaboration with it. We find the channel's coherent modes and whisper our meaning into them. We have added a crucial discipline, the marriage of intention with channel physics. A beautiful message in a vacuum is useless. The test of speaking is survival in the real, noisy world. This is the foundation of true engineering. Not just wishing, but causing a specific, reliable effect at a distance. Closing. So picture yourself back in the radio operator's cabin. The channel analyzer screen shows the messy frequency response of the reverberant room, with its peaks and nulls. You design your BPSK signal, choosing a carrier frequency squarely on a peak, well within the coherence bandwidth. You add a simple error-correcting code. You simulate it in the twin. The predicted BER is 0.001. You press transmit. In the other room, the decoder lights up. 101. Again. 101. Again. Out of 10,000 trials, 9,990 are correct. The error rate matches the prediction. You have not just made noise. You have communicated. You have caused a specific intended pattern of understanding to arise in a distant mind, using nothing but shaped vibrations in the single universal field. You have just learned to speak the universe's language. This is part 10.1.3, Speaking in Phi, Designing Messages that Survive. It is the third branch of Book 10.1, Language Fluency, the capstone of literacy. In our next session, we will step back and ask, how fluent are we, really? We will establish objective, measurable benchmarks for Phi literacy. We will define what it means to be a reader, an interpreter, a speaker. We will build the tests that separate skill from speculation, ensuring that everyone who claims to understand this craft can prove it. Remember, one field, Phi, with its infinite echoes in time, space, and motion. We are no longer passive. We are conversant. We have found our voice. Salam, and peace be upon you.